Underneath America's most productive farmland, the earth is disappearing. Not eroding, not shifting, collapsing. In parts of California's Central Valley, the ground is sinking 2 feet every single year. That's not a measurement error. It's not soil compaction from tractors. It's the land itself, thousands of square miles, dropping like an elevator with a cut cable. In November 2024, researchers at Stanford University published findings that should have made national headlines, but somehow did not. They discovered we have lost as much ground in the past 16 years as we did during the entire 50-year period before that. The Earth is accelerating its descent. In May 2025, California's Department of Water Resources issued a projection so stark, it reads like fiction. If this continues at current rates, the State Water Project, the system that supplies water to 27 million Californians, could see deliveries cut by 87% within 20 years. This is not just California's problem. This valley produces 40% of America's fruits, nuts, and vegetables. Your almonds, your tomatoes, your lettuce, all grown on land that is literally vanishing beneath the farmer's feet. Even if every groundwater pump in California shut off tomorrow, Stanford's models show the compaction will continue for decades, possibly centuries. The question is not whether the ground will keep sinking. It will. The question is whether we will still be able to grow food here when it does. To understand how catastrophically wrong things have gone, you need to understand how they are supposed to work. The San Joaquin Valley, the southern portion of California's Central Valley, spans 20,000 square miles. It is one of the most productive agricultural regions on the planet, generating over $50 billion in crops annually. For over a century, this productivity has rested on a foundation most people never see. Massive underground aquifers formed over millions of years as Sierra Nevada snowmelt percolated down through layers of sand, gravel, and clay. These aquifers are not underground lakes. They are porous rock formations. Imagine a giant sponge made of sand and clay, saturated with water. When you drill a well and pump, you are extracting water from the spaces between particles. In a healthy, sustainable system, the water you remove is naturally recharged each winter as rain and snowmelt seep back down through the soil. Groundwater pumping in the Central Valley began in the 1920s. By the 1970s, portions of the valley had subsided, sunk by as much as 28 feet. That is enough to swallow a 3-story building. But here is the critical context. That happened over 50 years. It was gradual, measurable. And when California completed the State Water Project aqueduct system in the 1970s, delivering surface water from Northern California, the subsidence largely stopped. The aquifers stabilized. For decades, the valley demonstrated what sustainable water management looks like, pumping balanced with recharge, slight fluctuations within acceptable ranges. This is how aquifers are supposed to behave. Water levels rise and fall seasonally. Clay layers compress slightly when water is removed, then expand when it returns, like a sponge being squeezed and released. The system has elasticity, resilience. Scientists at the United States Geological Survey have monitored these aquifers for generations. They understand the mechanics. They know the baselines. What's happening now does not match any of those baselines. In 2006, something changed. California entered a period of severe drought that would persist, with brief interruptions, for nearly 2 decades. Surface water deliveries from the State Water Project dropped dramatically, sometimes to zero. Farmers had 2 choices: let crops die or pump groundwater. They pumped. What Stanford researchers discovered using 16 years of satellite data, specifically interferometric synthetic aperture radar, INSAR, which can measure ground elevation changes with millimeter precision, is that the valley has subsided by a volume of 14 cubic kilometers since 2006. To put that in perspective, That is roughly equivalent to the total subsidence that occurred during the entire historic period from 1925 to 1970. Half a century of sinking compressed into 16 years. In some locations, the land is dropping more than 1 foot per year, year after year. The California Aqueduct, the concrete-lined canal that carries water from north to south, has developed what engineers call bowls. Sections of the canal have sunk so much that water pools there and cannot flow properly. Operators are now running water closer to the top of the canal's concrete liner, at operational limits. If subsidence continues, the canal could lose its ability to transport water entirely. The Friant-Kern Canal, another critical piece of infrastructure, has lost 60% of its flow capacity due to subsidence damage. Repairing it will cost $400 million. Over 4,200 residential wells have gone dry since 2013, and that is likely an undercount because many are not reported. In the past 5 years alone, farmers have drilled over 7,000 new agricultural wells, racing to go deeper as the water table plummets. This is not what slow geological processes look like. This is not normal aquifer drawdown. And every attempt to explain it as a temporary aberration has failed. The USGS sent teams to verify the satellite data using ground-based GPS stations and physical extensometers that measure soil compaction directly. The numbers matched. NASA's Jet Propulsion Laboratory analyzed the INSAR data for potential errors, such as atmospheric distortions, satellite drift, and processing artifacts. The subsidence was real. Stanford researchers built computational models to understand the mechanism. What they found was worse than anyone expected. It is not just the shallow layers. The problem is deep clay. Aquifers are layered systems. Near the surface, you have coarse sand and gravel. These materials compress and rebound relatively easily when water is removed and then restored. But deeper down, sometimes thousands of feet underground, lie thick layers of fine-grained clay. These clays hold water, but they release it slowly, reluctantly. When groundwater levels drop, these deep clay layers begin to compact under the immense pressure of the overlying rock and soil. Unlike sand and gravel, clay does not bounce back. When clay particles are squeezed together, they form new bonds. The space between them closes permanently. It is not a sponge being squeezed. It is a sponge being crushed into a dense, impermeable mass. Stanford's 2024 study determined that over 90% of the subsidence in the Central Valley is coming from these deep clay layers. And here is the truly alarming finding. These layers will continue compacting for decades to centuries after groundwater levels stabilize. Think about that. Even if California achieved perfect water balance tomorrow, even if every pump shut off and aquifers were fully recharged, the damage already done means the land will keep sinking. The clay layers 1 mile underground are collapsing under their own weight, and there is no mechanism to reverse it. In 2025, Stanford researchers published follow-up modeling that quantified this delayed response. Their projections show subsidence continuing well into the next century, under even the most optimistic recharge scenarios. The only way to significantly reduce future subsidence is managed aquifer recharge, deliberately flooding fields during wet years to raise water tables as quickly as possible. But there is a problem. There is not enough water. California's surface water supplies are finite and increasingly strained by climate change. The Sierra Nevada snowpack, the natural reservoir that feeds both rivers and aquifers, is declining. Even in wet years, there is not enough surplus water to flood the entire valley. Managed aquifer recharge requires taking productive farmland out of cultivation and converting it to recharge basins. For an agricultural region already under economic pressure, that is a devastating choice. Kings County, one of the hardest hit areas, was placed on probation by state regulators in April 2024 for failing to develop an adequate groundwater sustainability plan. The county's response was blunt. They said, "We have no other economy." Kings County becomes a ghost town. This is the trap. The land is sinking because of excessive pumping. Stopping the pumping requires either destroying the agricultural economy or finding water that does not exist. And even if water materialized, the subsidence will not stop. It will just slow down over the course of multiple human lifetimes. The consequences are cascading through every system that depends on stable ground. Infrastructure first. The California aqueduct damage is estimated in the billions for full repair and reinforcement. But you cannot simply fix a canal that is built on land that will not stop sinking. Any repair is temporary, a bandage on a wound that keeps opening deeper. A $400 million repair project for the Friant-Kern Canal is already underway. But engineers acknowledge it is buying time, not solving the problem. For farmers, the crisis is immediate and expensive. Drilling a new well that reaches viable water depths now costs over $1 million. The waiting lists for drilling companies exceed entire growing seasons. Some farmers are going 2,000 feet deep, depths that were unthinkable a generation ago. At those depths, they are reaching water that recharged thousands of years ago, water that is effectively fossil groundwater and will never be replenished on human timescales. There is a dark economics to this. When your neighbor drills deeper, they are pulling from a shared resource. It has been called drinking your neighbor's milkshake. Every new deep well makes everyone else's wells less effective, creating a race to the bottom that destroys the aquifer for everyone. For the 4,200 households that have lost access to water, the impact is existential. These are predominantly low-income, rural communities with no backup systems. Families are hauling water for basic needs or abandoning homes entirely. And the USGS acknowledges this count is low. Many dry wells go unreported because residents simply leave. The economic ripple extends far beyond California. This valley produces 80% of the world's almonds, 95% of America's processed tomatoes, and massive percentages of walnuts, pistachios, grapes, and leafy greens. If production collapses, or even significantly contracts, global food prices will respond. Then there is the water supply. 27 million Californians depend on the State Water Project. The system is already operating at reduced capacity due to subsidence damage. The May 2025 projection of an 87% reduction by 2043 assumes current subsidence rates continue, but current rates are accelerating. Urban California, including Los Angeles, San Diego, and the San Francisco Bay Area, could face water rationing that makes current restrictions look trivial. And here's the part that makes this irreversible. Aquifer storage capacity is being lost. When clay layers compact, they do not just squeeze out water, they permanently destroy the ability to store water. The valley is losing its natural reservoir. Even if climate patterns shifted to deliver more rain, even if California built infinite surface storage, the underground storage that made this valley's agriculture possible is being crushed out of existence. California's policy response came in 2014 with the Sustainable Groundwater Management Act, SGMA. It required local agencies to develop plans to achieve groundwater sustainability by 2040. On paper, it looked comprehensive. Local control, science-based targets, clear deadlines. The reality has been more complicated. Many groundwater sustainability agencies, the local bodies tasked with implementation, developed plans assuming that stabilizing water levels would stop subsidence. That assumption appears in plan after plan. Once we balance pumping with recharge, the sinking stops, the aquifers recover, crisis averted. Stanford's 2025 research directly contradicts that premise. The plans are built on a misunderstanding of the physics. Stabilizing water levels will slow the rate of new subsidence, but the damage already done to deep clay layers will continue expressing itself for generations. The alternative, managed aquifer recharge, requires resources most agencies do not have. During wet years, they would need to flood thousands of acres of farmland to deliberately percolate water down to recharge the aquifer. Identifying which land to flood demands complex hydrogeological modeling. Acquiring that land, or compensating farmers for taking it out of production, requires funding many agencies lack. And the water itself, the surplus needed for recharge, is becoming increasingly scarce as climate change reduces Sierra Nevada snowpack. Recharge at scale is not simply a technical fix, it is a resource and political challenge. Some agencies are pursuing targeted approaches, focusing recharge efforts on areas with critical infrastructure like the aqueducts, and accepting that other areas will continue subsiding. It is a form of triage, saving what can be saved and abandoning what cannot. The agricultural community is divided. Larger, wealthier operations can afford deep wells and more efficient irrigation technology. They have the capital to adapt, at least temporarily. Smaller operations, particularly in already marginal areas, face impossible economics. Taking land out of production to comply with SGMA means losing income with no guarantee the sacrifice will work. The sector is split between those who can buy time and those who cannot. Kings County's reaction to being placed on probation captures the desperation. Compliance might mean economic death. Non-compliance means escalating fines and potential state intervention. There is no good option. Every attempt to manage this crisis reveals new dimensions of the problem. More monitoring means more alarming discoveries. As INSAR coverage improved and analysis became more sophisticated, researchers found subsidence in areas previously thought stable. The affected area keeps expanding. Deeper drilling, the adaptive response by farmers, accelerates compaction of exactly the deep clay layers causing most of the problem. Each deep well makes the long-term subsidence worse while providing short-term survival for individual operations. The tragedy of the commons is playing out in real time, thousands of feet underground. SGMA requirements, designed to force sustainability, are creating economic pressure on the poorest farming communities first. The regions most dependent on groundwater, with the least access to surface water alternatives, are the ones being told to cut back. The environmental justice implications are staggering. The communities that contributed least to the problem and have the fewest resources to adapt are bearing the heaviest burden. Climate change is not helping. Declining Sierra Nevada snowpack means less natural recharge water available, even before human allocation. Drought cycles that used to occur every decade or two are becoming more frequent and severe. Each drought triggers a spike in pumping, which triggers accelerated subsidence, which damages infrastructure, which reduces water delivery capacity, which forces more pumping. A death spiral. Recent research on continental drying, the global phenomenon of groundwater depletion, suggests California's Central Valley is part of a much larger crisis. Aquifers worldwide are being depleted faster than they can recharge. The solutions that might work in California would require water from somewhere else, but those other regions are facing their own crises. And then, there is the mathematical certainty embedded in models from Stanford. Stop all pumping today, and subsidence continues for centuries. The only intervention that significantly helps, massive sustained managed aquifer recharge, requires water that does not exist in sufficient quantities. It is a perfect trap. The damage is done. The solution requires resources we do not have. And every day we delay, the deep clay layers compact a little more, irreversibly destroying the aquifer system that made this valley productive in the first place. The ground beneath America's most productive farmland has dropped 28 feet in a century. In the past 16 years alone, it sank as much as it did during the entire 50-year period before that. The acceleration is undeniable. The mechanism is understood. The future is mapped. Stanford researchers have modeled what happens next, and what they found should concern anyone who eats food. Even if every pump shut off tomorrow, the compaction will continue for decades, possibly centuries. The clay layers a mile underground do not respond to water policy. They are collapsing under their own weight, crushing like a sponge that has been wrung out and can never expand again. By 2043, the system that delivers water to 27 million Californians could see deliveries cut by 87%. That projection assumes subsidence continues at current rates, but current rates are accelerating. The infrastructure we built to move water is failing because the ground it is built on will not stop moving. The questions facing America's breadbasket are not technical anymore. They are existential. Can we grow 40% of the nation's produce on land that is permanently sinking? What happens to global almond supplies when the Central Valley, which grows 80% of the world's almonds, loses access to water? How do you feed 27 million people when your water delivery system is compromised by ground that will not stabilize for generations? The farmers drilling 2,000 feet deep, reaching water that fell as rain when mastodons still walked California, are buying time measured in years, maybe decades. Below them, the clay is still compacting. Above them, the snowpack that is supposed to recharge everything is shrinking. There are no villains in this story, just farmers trying to survive, communities trying to adapt, engineers trying to manage systems built on assumptions that are no longer true. Everyone did what made sense at the time. Everyone followed the rules until the rules changed. The question is not whether the ground will keep sinking. Geology does not care about our deadlines, or our economic needs, or our sustainability plans. The clay will compact until it reaches a new equilibrium, and that equilibrium is denser, smaller, with less space for water. The question is, what we will do when the foundation of America's agricultural miracle finishes collapsing. When the wells run dry, not because there is no water, but because there is no room left underground to hold water. When the aqueducts cannot deliver because they are too damaged by ground that will not stop moving. Where will America's salad come from then?